Last topic of this unit, we look at how to compare motion of objects, or the motion of objects between different frames of reference and different perspectives, what we call relative motion. So first thing that we need to define is what's called a reference frame. A reference frame is a perspective or environment from which we make observations and measurements. So for example, if we look at the train right here, the reference frame of this person in the red dress would be the environment of the train. While the reference frame of the person in the yellow shirt would be the ground outside of the train. So as a result, the perspectives of the two people are different. They have different observations about their motion. So the person in red says that they're standing still because relative to their reference frame, the train, they are standing still. They are not moving. While relative to the person on the ground in the yellow shirt says that the person in red is moving, because relative to the ground, and thus the person in the yellow shirt's perspective, the train is moving. So we start off again by defining inertial reference frames. An inertial reference frame is where the environment one occupies moves at a constant velocity. So if this train right here were accelerating, that would not be considered an inertial reference frame, whereas if the train is moving at a constant velocity, that would be considered an inertial reference frame for a person in red. So inertial reference frames in the laws of physics. So all inertial reference frames are equally valid, and that there is no one true correct frame from which to judge an object's motion. So what we mean by this is that both opinions here are not really opinions, but they're actual facts. And each fact is equally valid based on the reference frame that the person is in. So the person in red, they say that they are at rest and standing still because on the train they're not moving. This is a valid opinion because relative to the train, our person in red is standing still. While on the other hand, the person in yellow says that the person in red is moving because relative to the ground, which is the person in yellow's reference frame, the train is moving. This is also an equally valid statement. Both statements are equally valid and equally correct based on the perception of both persons based on their inertial reference frames. So what we say is that the laws of physics remain the same in any inertial reference frame, meaning that the laws of physics are equally valid in the reference frame of the train as they are for the reference frame of the ground and the person on the ground. So to illustrate this, okay, suppose that we had a windowless train that our person was standing on. If this person was born on this windowless train, and we also make the additional assumption the train's perfectly steady, so there's no bumps or anything like that, the person would not be able to distinguish if the train was moving or the outside was moving. So they were born on a windowless train, and then let's say we add a window in here. If the person were to look out, and again this train is perfectly steady, that person would have no way of distinguishing if the train was moving or the outside was moving. Again, both are perfectly valid statements. So actually, what we could also say here is that if the person in red was to attempt an experiment in order to determine if the train was moving, if the train is an inertial reference frame, there would be no way for the person to determine, and thus there would be no experiment that our person in red could set up. If our person in red were to drop a ball, or a person in red were to walk from the front of the train to the back of the train and vice versa, they would feel the exact same way as if they were walking on the ground or dropping a ball on the ground. So as a result, there would be no way that a person could distinguish whether the train was moving or whether the outside was moving. Hence, we say the laws of physics remain the same in any inertial reference frame. Both statements are equally valid. So now we move on to moving between reference frames, okay? So if you want to determine the speed of the red person relative to the person on the ground, provide some information about their relative speeds, we can proceed as follows, okay? So first, we need to write down the customs. First, what we do is we write down the velocity of an object O relative to some reference frame R as VOR, the velocity of O relative to R. For the train example, the object O outside of the train moves at 60 miles per hour west relative to the train, meaning that a person on the train, suppose our train were moving at 60 miles per hour east, a person on the train who says that they're standing still would thus see a person in yellow moving at 60 miles per hour west relative to the train. So what we would write is that the velocity of the object, say our person in yellow, relative to the train would be negative 60 miles per hour because the negative 60 corresponds to the person in red on the train seeing the person in yellow moving at negative 60 miles per hour to the west. So here's the procedure that we follow if we want to move between reference frames. So if I'm a scientist S measuring the velocity of an object O relative to me, and O is in a reference frame E, I would first write down the velocity of the object O relative to its reference frame. Okay? Secondly, I would write down the velocity of the reference frame E relative to me, VES, the velocity of E relative to S, the scientist. So now what we're going to do is we're going to add the two velocities together to obtain our velocity of the object relative to the scientist, myself. So the velocity of the object relative to the scientist is going to be equal to the velocity of the object relative to its environment, its reference frame E, plus the velocity of the reference frame relative to the scientist. So all of this seems a little bit tricky, but really nothing amounts to more than switching between reference frames and then adding the numbers at the end of the day, adding two numbers at the end of the day. So let's get a little bit of practice to see what this looks like in a practical example. So a plane is moving at 112 meters per second north relative to the ground when a passenger gets up to use the bathroom, heading to the back of the plane at 6 meters per second. This person really has to go. 6 meters per second relative to the plane. Relative to someone on the ground, how fast is the passenger moving? So first what we do is we determine the speed or velocity of our passenger relative to the plane. Okay? So what we can write down is that the passenger relative to the plane, their original environment is 6 meters per second, but since they're heading towards the back, aka south, we'll take that to be south, and hence negative. So the velocity of the person relative to the plane, what we call VPP, will be negative 6 meters per second. Next, what we're going to do is we measure the velocity of the plane relative to the observer on the ground. So we know that the plane relative to somebody on the ground is moving at 112 meters per second north. So we write down that the velocity of the plane relative to the ground, the VPG, the PG is a little bit hard to see here, is 112 meters per second. Okay? So now the last thing we do is we combine the velocity of the person relative to the plane and the velocity of the plane relative to the ground to obtain the velocity of the passenger relative to the ground. So that means we just combine our two velocities. The velocity of the person relative to the plane plus the velocity of the plane relative to the ground equals the velocity of the person relative to the ground. So we get negative 6 meters per second plus 112 meters per second equals 106 meters per second. This makes sense because as our person is on the plane, they are still going to be moving forward and hence have a positive velocity. But because in the plane's original environment they're heading to the back of the plane, their velocity is going to be a little bit less than the velocity of the plane measured relative to the ground. A nice little mnemonic that we can see here is if we look, when we add the two velocities, the intermediary letters cancel out, and we're going to be left with just the outer letters, which is the velocity we want. So the person remains and the ground remains, which makes sense because we're looking for the velocity of the person relative to the ground. The intermediary letters, plane and plane, cancel out. So again, to reiterate, what we're going to do is we determine the velocity of our object relative to its original environment. We determine the velocity of the environment relative to the observer or the reference frame we're interested in, and then we add the two velocities together. And these are the main ideas for moving between reference frames.